This is part 3 of the AQA A-level chemistry topic, amount of substance. In this video, we're going to be focusing on empirical formula and associated chemistry. So, as always, I'm going to recommend that you pause at each section, try each task, and then you can review and see how you've done. And if there are things that aren't going so well, it means you can then look into them further and go and ask for help where needed. So, starting off with a basic introduction to empirical and molecular formula, great place to start is definitions. And it is absolutely vital that you learn these definitions as they are written, or all of the detail included. Empirical formula is the simplest ratio of atoms of each element in a compound. Molecular formula, the actual number of atoms of each element in a compound. It's very unlikely you'll be asked to define them, but you need to understand those definitions so that you can apply that knowledge to the questions and the calculations that follow. The questions on the right hand side here are much simpler than you would get in the exam, but it's a good way of checking your understanding. So try to work out the empirical formula of the 3 compounds that have been provided. So in the first one, I've got a ratio of 3 to 8. Propane, it cannot be simplified. So we have C3H8. Butane, however, we've got C4H10. 4 and 10 are both divisible by 2. So the empirical formula, the simplest ratio, is C2H5. And aluminium chloride, Al2Cl6. Both of those numbers are also divisible by 2. So that goes down to AlCl3. Predominantly, however, empirical formula is based around calculations, and the majority of this video is going to be focused on looking at examples. Now, what I have here is a worked example, and you can see we're going through 5 different steps. Constructing a table that you've got to learn the structure of, adding in the masses, adding in the atomic masses, calculating moles, and then working out the mole ratios. And I'll talk about those as we go through the calculations. But every single step, absolutely vital. Being able to do that with confidence comes from practice. And once you've completed this video, one of the best and most effective ways of testing yourself on empirical formula is to do lots of past paper questions. Okay, so let's take the first example. We've got magnesium and oxygen. We are told that we've got 60% magnesium. I'm going to draw out my table. I've got mass, atomic mass, moles and ratio. It never changes. I've got the 2 elements involved up at the top. And I've then put my 60% magnesium in. Because this is percentage by mass, oxygen therefore must be 40. Now for the atomic mass, I go to the periodic table. I look at the mass number. Magnesium is 24.3, oxygen is 16. And then I've got to use my mole calculation that we discussed back in video 1 of this topic. Number of moles is mass divided by atomic mass. One of the great things about this table is mass is over atomic mass, and it leads in to the moles. So I do 60 over 24.3, I do 40 over 16, and I get 2.5 for both of them. Now, for the simplest whole number ratio, easiest way to do that is to divide both of those by the smallest. In this case, both of them are the smallest, so I divide them both by 2.5. That gives me a 1-to-1 ratio, 1 Mg, 1 O, formula MgO. On the next one, I've got 36% beryllium. I put my Be and O in. I construct my table. If it's 36% Be, it must be 64% O. I put my ARs in. I do my N is M over AR calculations, and I get 4 to 2. 4 to 2 is not the simplest whole number ratio. Both of them are divisible by 2. So that takes me down to 2 to 1, and that gives me a formula of Be2O. For the next example, it's a hydrocarbon, 8% by mass. So we're adding in some organic knowledge here. We know that a hydrocarbon is made of carbon and hydrogen only. We also know that if 80% of that hydrocarbon is carbon, 20% must be hydrogen. We put the atomic masses in direct from the periodic table. We do N is M over AR, and that takes us to 6.6 and 20. That's not the simplest whole number ratio. We divide them both by the smallest and we get 1 to 3. The empirical formula is CH3. And then we have another one where we're actually told both of the elements and their masses. So you'll note this is not a percentage by mass. I've got H, I've got O. I put my masses in, 4 and 32. I put my atomic masses in, hydrogen is 1, oxygen is 16. M over AR takes me to 4 and 2. They're not the smallest whole number ratio, so I can divide both of them by 2. I get 2 H's, 1 O, I get H2O. On this question, you can see there's space for a bit of extra information. See how you do. This time we've got 24 grams of calcium, 5.6 grams of nitrogen. So I've constructed the table and I've put those masses in. I go to my periodic table and I find that calcium is 40.1 and nitrogen is 14 for the atomic mass. I can then go ahead and do exactly what I've done on all of the others and I calculate the number of moles, 0.6 and 0.4. I need whole number ratios, so I'm going to divide both of those by the smallest because that's what I always do. But we hit a problem, 1 to 1.5. I can't have 1.5 calciums in a molecule. I need to get to a simplest whole number ratio. So, easiest way to do that is to double both of those numbers. That takes me to a 3 to 2 ratio, Ca3N2. Moving on, we've got P and Cl. We're seeing the pattern now. Hopefully you're trying this and then reviewing your answer. Hopefully you're constructing that table. You're putting in the two masses that have been provided. You're finding the atomic masses that are on the periodic table. And then you're calculating number of moles. We get to 0.01 and 0.03. Divide both of those by the smallest, 0.01. That takes us to a ratio of 1 to 3. We have PCl3. Next one, we've got mercury forming mercury sulfide. Have a go at that and then check your answer. Read it carefully. So I draw out my table. I've got my Hg, I've got my S. I put my 4 grams of mercury in and then there's potential for error. If you read the question carefully, it tells us that we're forming 4.64 grams of mercury sulfide. That means we don't put 4.64 here, we put 0.64 in, because the law of conservation of mass tells us the mass of mercury plus the mass of sulfur will equal 4.64. At that point, I go through the process exactly the same as I've done in all of the other examples. I take my atomic numbers, I divide my M by AR to get moles. In this case, they're both 0.02. Divide them both by 0.02, and we get a ratio of 1 to 1. We get HGS. Let's try the next two examples. And you can see here we've got phosphorus with chlorine again, but let's take a look to see if there's any difference. In the first instance, I draw out my table. I've got my mass of phosphorus, 0.31, but we've got the same situation as we had on the previous question. I'm making 2.1 grams of phosphorus chloride, which means I've got 1.7 grams of chlorine. I put my atomic masses in, 31 and 35.5. I divide my M by AR in each case. I get 0.01 and 0.05. Divide both of those by the smallest. That takes me to a 1 to 5 ratio, and we have PCl5. And we're seeing a similar pattern on the next one. We draw out the table. We then put the masses in. It is 5.05 grams of chlorine, because once again, we're told the total mass of the compound. Then, atomic masses in. Divide by number of moles, and we get 0.1 to 0.15. Divide by the smallest, and we get 1 to 1.5. We've seen this already. We can't have 1.5 chlorines, so we need a whole number ratio. Multiply them both by 2, and we get Fe2Cl3. Moving on to combustion analysis now, which takes many of the skills and some of the straightforward maths, puts it together in a different way. There's a worked example. I'm going to recommend you try that worked example, pausing the video as you go, and we will take a look. These aren't incredibly common questions, but you do need to be prepared for them. Okay, so looking at the information that we've been provided with, I have got 2.64 grams of carbon dioxide and 1.08 grams of H2O. Now that means I can work out my moles of CO2, 0.06. I can work out my moles of H2O, 0.06. From there, I can work out how many moles of C I needed to make 0.06 moles of CO2. There's one C in a CO2, so it's 0.06 moles of C. To make 0.06 moles of H2O, I would need 0.12 moles of H, because there's two H's in every H2O. Now from there, I can work out my mass of carbon and mass of hydrogen. That's moles multiplied by atomic mass. I've got 0.72 grams of carbon and 0.12 grams of hydrogen. That's a total of 0.84. Now I've got 1.16 grams of a sample, so the rest of it is another element. Often it will tell you that it's oxygen when these questions come up. Actually, because there is no other product of combustion here, the other element must be oxygen. So I've also got 0.32 grams of O. Now, once I've got each of those masses, and I've already actually got my moles of C and moles of H, I can use that mass of oxygen to calculate my moles of O, and I get 0.06, 0.12, and 0.01. C6H12O. However, we've fallen into a pitfall, so I wanted to watch what we're about to do very carefully. I've taken the molecular mass of oxygen as being 32, but we're dealing with the individual atom of O. So actually, we need to divide by 16. So what we actually end up with is 0.02 moles of oxygen. We have the empirical formula C6H12O2. Now we're going to finish off with a few more examples, including some water of crystallization questions. Try these two and then review your answers. So in the first example, the major difference from what we've seen earlier is there are three different elements included. So we've got to have C, H and O. But I draw the table as normal. I put the masses in. I find the MRs. Calculate the number of moles, M over AR, and then divide each of them by the smallest. I get 1.5, 3.5 and 1. I need a whole number ratio. I multiply that ratio by 2 and I get C3H7O2. The question also asks for the molecular formula, and this is the empirical formula. Sometimes it's the same, sometimes it's not. Now, if I took that empirical formula and calculated its MR, it comes to 75. But the question tells us the MR is 150. So actually I need to double this molecule. Instead of C3, I need C6. H7 becomes H14. O2 becomes O4. So the empirical formula is different to the molecular formula. On the next question, we have got B and H. I draw out my table. I put my masses in. I've had to calculate the hydrogen here by looking at what's left after the 78.6% boron. I put my atomic masses in, 11 and 1, calculate my moles, and then work out my ratio. Again, I've got an empirical formula here, BH3. That would have a molecular mass of 14, but the question tells us the compound has a molecular mass of 28, so we're doubling it. The molecular formula is therefore B2H6. And then we're going to move into some water of crystallization questions. Have a go at this one and then we'll work through. So pause. And now let's carry on. Now you can use the the empirical formula model to do these, but you draw your table in a slightly different way. Instead of individual elements, you will put your compound and your water in two separate columns. And then you draw the table exactly as you did. Then you add the masses exactly as you did. Then you find the molecular masses of barium chloride and water using the periodic table. We get 208.3 and 18. When I do M divided by MR in each case, that takes me to 0.41 and 0.819. My simplest whole number ratio is 1 to 2. So that means for every barium chloride, I have 2 waters. BaCl2.2H2O. And another example of that type of question. Pause, see how you go. So we draw out the table. We put in our mass of copper sulfate. In this particular question, we've got to work out the mass of water. We know we had 0.556 grams of the copper sulfate, so the remainder of the 0.869 is water, 0.313. I put my MRs in, and then I do my mole calculations, 0.0035, 0.0174. Let's divide them both by the smallest, 0.0035, and it takes me to a ratio of 1 to 5. That means that my formula is CuSO4.5H2O. That takes us to the end of part 3 of this topic. Thank you for listening. Goodbye.